So Chapter 10 is a study of thermodynamics, and thermodynamics is a study of heat and energy. And we're going to look at both types of energy that you've been exposed to, I'm sure, in other classes, which is kinetic and potential forms of energy. And kinetic energy is energy that is due to motion. In chemistry, this is most often referred to as thermal energy, because anytime we measure the temperature of something, we're really measuring the kinetic energy of the atoms and molecules present in that sample. Then we have potential energy. In physics, this is due to position, and in chemistry, it's more due to composition. Chemical energy is associated with positions of electrons and nuclei and the bonds that exist between all those. Now, we've used the terms endo and exothermic very briefly back in a previous chapter, and we're going to look at these in a little bit more detail as we go through the chapter. Let's take a look at kinetic energy. Again, this is the energy associated with motion, and it's governed by both mass and velocity, just as most kinetic energy is. And we see that kinetic energy is equal to 1/2 mv squared. Now, the units that we use here are very important. We want to make sure that our mass is in kilograms and our velocity is in meters per second. So we have 1/2 mv squared. And all we're really worried about here is our units. So we have kilograms for our mass unit. We have meters per second for our velocity unit, and that gets squared. So we end up with kilograms, meters squared per second squared, and this is equal to this is the units of the SI unit of energy, the joule, which we just use as a capital J. Now, the joule is actually a fairly small unit, and most of our chemical reactions either absorb or release kilojoules of energy, so we very rarely see joules as just straight joules as energy units. But we have another common unit that we use. It's non-SI, or I should say it's non-standard, but it is SI actually. And this is the calorie unit, and 1 calorie is equal to 4.184 joules, and 1 big calorie there is equal to 1,000 calories. The difference being this capital C right here, which tells us that we have a big calorie, and these are actually called little calories. So you have big calories and little calories, and 1 big calorie is 1,000 calories, or it's also equal to a kilocalorie. So that was kinetic energy. Let's take a look at potential energy. This is energy associated with position in physics, and this becomes associated with gravity, height, and mass. And this description doesn't really apply very well to chemistry. So the potential energy in chemistry is primarily stored in bonds and the types of bonds present and the energies either required to be absorbed to break bonds or the energy released when certain bonds become formed. And when energy is absorbed or released in a reaction, we have something that is called the heat of reaction. And this is where we bring up our terms endothermic and exothermic. So these refer to the heat of reaction for any particular given reaction. So we need to reference what is considered out, because exothermic means heat is going out, and endothermic means heat is going in. Well, really what we need is what. Heat is going out of what or into what. And so everything that we do in thermodynamics, as far as a reference, we reference everything around the system. And so the substances being studied are called the system, and everything else is called the surroundings. So only the atoms and molecules involved in a reaction are the system. Everything else around it is called the surroundings. So again, in chemistry, we reference everything to the system. So if the system gains heat, the energy is positive, so this is endothermic. And if a system is giving off heat or losing heat, then the energy is negative, and this is what we call exothermic. Heat is going out, the system is losing that heat, so energy is negative. Now we use the symbol Q to represent heat, and we use the symbol W to represent work. And we'll see these get used off and on as we go through the chapter. Now, in the first law of thermodynamics, one of the things we have to realize is that the total energy of the universe is constant. Energy is neither created nor destroyed. It can only be transferred from one object to another, and it can be transformed from one form to another, and one of these forms includes mass. So you can take mass and turn it into energy. Now, we use the symbol E to represent the internal energy of a system, and this is just the sum of all the kinetic and all the potential energies of all the particles in a particular system. This is not particularly easy to use or calculate. It's much more conceptual, something we need to think about conceptually as opposed to calculate. Now, internal energy is also something that we call a state function. And what a state function means is that anytime we have a change in that state function, it's dependent only upon the initial state and the final state. Let's take a look at a graphic representation of a state function that's completely non-chemical here. And so here we've got two different paths to the top of a mountain, and we've got our base that's down here at 0 feet. So we've got a long path that's a little bit more winding that starts down here, and our shorter path that starts here. So for our longer path, we go around this way, and then we zip back here, and then come up and go over and around this way, and finally we get up to the very top. And that route is 12 miles long, so considerably longer than the short route, which involves a little bit of meandering, but not nearly as much because it only takes 5 miles to get up that path there. Well, notice the difference in elevation here for both of them is still 10,000 feet, which means that the elevation here would also be a state function. It doesn't matter which of those paths you take to go from the base to the summit there, you're going to have a change in elevation of 10,000 feet. So the elevation here would be considered to be a state function, or the change in elevation. Now, the distance traveled, that is not a state function because that does depend on which of these two paths you take. On this last slide, as I mentioned, calculating the actual energy, internal energy of a system and the surroundings can be quite difficult, and it's not very practical, particularly for this level class. We can, however, measure a change in these energies fairly easily, and so we say that delta E is equal to the E of the final condition minus E of the initial condition. Or an easier way to put that is that delta E is equal to the energy of the products minus the energy of the reactants. And one of the other things that we'll see with energy is that delta E is equal to the amount of heat either into or out of the system plus the amount of work that the system does on something or has done on itself. And then down there at the bottom we have our different signs depending on whether energy is gained or lost, whether work is done on the system or by the system, and whether energy is flowing into the system or out of the system. We're going to start off on some more thermodynamics here, looking at some sign conventions, a slide that we had on the previous lecture, but look at it in a little bit more detail here. So we have our different symbols for that we use in thermodynamics. We have Q for heat, we have W for work, and E for energy, and delta E for a change in that internal energy. And we want to take a look at those signs. Anytime we have a positive sign on either Q, W, or delta E, it indicates that the system is gaining those things. So it's either gaining heat, work is done on that system, or energy is flowing into that system. And if we take a look at the negatives, the negative for heat would mean that's losing thermal energy, so something is cooling down or giving off heat. A negative for work would be that the system itself is doing work on something else, or in terms of delta E, energy is flowing out of that system. Let's just take a look at a reaction here. We have carbon plus oxygen goes to CO2, so this might be something like burning a piece of charcoal, burning a piece of carbon there. And if we look at the differences in the energy, we see that the internal energy of the solid carbon and the oxygen gas is actually higher than what we have for carbon dioxide gas, the product. And so since the internal energy of that system went down, then delta E for that would be less than 0 or negative, and the system actually became more stable by doing that. If we take a look at the energy flow, the energy that it lost, so that negative delta E indicates that that system lost energy. And where did that energy go? Well, it had to have gone from that system into the surroundings. So the delta E system would be negative, indicating that the system lost energy. If we were to look at a delta E for the surroundings there, then they would be positive, positive delta E, because the surroundings would have gained energy. So it just depends on your point of view whether something is negative or positive. Now, if we take a look at how heat and work are related, or how we can use them, we know from heat that heat moves from an area of high heat to one of low heat, sort of like water does. So if you have high water in one area and low water in another, and if they're connected and water can flow, then water would flow from the higher point to the lower point until the 2 points reach the same level. And heat does the exact same thing. So heat will level itself out in a thermal equilibrium. So if you took 2 pieces of metal and one was hotter than the other and put them together, heat would flow from the hotter object to the object with less heat until they reach the exact same temperature. So heat flows spontaneously. When we say spontaneously, we mean without any additional energy, so we don't have to force heat to go from hot to cold. So that's its spontaneous direction of flow, just like water goes from a high pressure to a low pressure, or from a high area to a low area. Heat flows from hot to cold. Now we can force heat to go opposite the direction it expects to go. We just have to do work on that system to make heat go that way, and we do that every day. Anytime you use a refrigerator or a freezer, or anytime you're trying to make something cold, you're taking heat from an area that has less heat and putting it into an area that has more heat. So this is our way of removing heat, is to use work to force heat to flow in a direction it doesn't want to do spontaneously. Now, when a system absorbs or loses heat, its temperature is going to change. One of the things we need to worry about, though, is how much is that temperature going to change, and it really depends on the material. Now, how do we measure the amount of heat that goes in and out of a system? Well, we actually measure the temperature. The key, though, is that heat and temperature are very different things. And so one of the properties that we need to consider is how much heat is required to raise an object's temperature. And again, this is dependent upon the object's makeup. And this property is called that material's heat capacity. Now, heat capacity is expressed as either molar heat capacity, which is the amount of heat needed to raise 1 mole of that substance 1 degree Celsius, or it'll have specific heat capacity, which is what we use more often than not, and we use the symbol C there. I think our book uses a C little s for specific heat capacity, and this is the amount of heat required to raise 1 gram of a material 1 degree Celsius. Now, both of these quantities are intensive properties, meaning it doesn't matter how much material we have, the value of those 2 heat capacities is going to be exactly the same. And as you can imagine, since specific heat capacity is per 1 gram and molar heat capacity is per 1 mole, the relationship between those 2 heat capacities is nothing more than the molar mass of that material. So let's take a look at specific heat capacity, because again, we do use that most often. It's used to quantify the amount of heat transferred based on the mass of the material and the temperature change. So again, we said the specific heat capacity is in fact a intensive property. So the heat capacity doesn't change, but the amount of heat needed does in fact change based on the mass. It's going to take more heat to change the temperature of a large mass of material as opposed to a small mass. So we have a nice equation there that relates all of those things together, and heat in joules, which we'll call Q, is equal to the mass in grams of the material times the specific heat capacity, which has units of joules per gram degrees Celsius. So gram and degrees Celsius are in the denominator, joules in the numerator there. And we multiply that by delta T, which is the temperature change from where it started to where it finished. So here's an example we'll work out in class. I guess, well, I'll take that back. We'll work it out right here. We want to know how much heat is absorbed by 15 grams of water in raising its temperature from 20 degrees Celsius to 50 degrees Celsius. Now, the specific heat capacity of water is 4.184 joules per gram degree C. Very often you'll also work this out in calories, and specific heat capacity of water is really nice. It is 1 calorie per gram degree C, but we're doing this one in joules. So we've got our equation. We have Q, the heat, is equal to C times M times delta T. And so our specific heat is 4.184. And then we have our mass, 15 grams, our delta T, 30 degrees Celsius, because we're going from 20 to 50. And we get an answer of 1.88 times 10 to the third joules. And if we take a look at how the units work out, we can see that our grams cancel out right here, out of there, and our degrees Celsius cancel out right there, and it leaves us with only a single unit left, joules, which is good because that's what I was looking for, was a heat, and heat can certainly be expressed in joules. Now, we mentioned earlier that heat always has a direction of flow from something hot to something cooler. So when we have a situation where we have two objects of different temperatures and they come in contact with each other, we're going to have an exchange of energy if there's an energy imbalance present. So let's imagine that we take a warm block of metal and we're going to place it into some water that has a lower temperature. Now, since the metal is hotter, we can see that the heat is going to move out of the metal and into the water. So the metal is going to cool off and the water is going to heat up. And the amount of heat gained by the water must be equal to the amount of heat lost by the metal. Now, they may have different changes in temperature, but the total amount of heat gained and lost has to be exactly the same. So that means that Q of the metal, so the heat of the metal, has to equal negative Q of the water. And the reason we have opposite signs there is because the metal is losing heat and the water is gaining heat. So because one's gaining and one's losing, they're going to have opposite signs as far as the heat, but the value of the heat is going to be the same. So let's kind of relate this to this concept of system and surroundings. So we can have that Q of the system is equal to negative Q of the surroundings. So we're going to make our system the metal, since that's what we heated up, and then we put it into the water. So we know that Q of the metal is going to equal the negative Q of the water. So what that means is that the mass of the metal times the specific heat of the metal times the delta T of the metal is equal to the mass of the water times the C of the water times delta T of the water. What I'm actually missing here, as I just noticed, is that I'm missing a negative sign here for negative because I have a negative heat. Let's take a look at an example, and we'll work this one out in class. A block of copper of unknown mass has an initial temperature of 65.4 degrees Celsius. We're going to take that, we're going to immerse it in a beaker of water that has a mass of 95.7 grams, the water, and the water is at 22.7 degrees Celsius. The two substances reach thermal equilibrium with temperature of 24.2 degrees Celsius. What is the mass of the copper? And the specific heat of copper is 0.385. This is something we would get on a table, and it's something you would normally be given. So we've talked a lot about heat so far. Let's go to that other side. Let's take a look at work. One of the most common types of work that we see in chemistry is pressure volume work. So if we look at pressure, pressure is really a force, and it acts against the sides of a container that might be sealed. Now, if a part of that container can move, so as an example, something like a piston, then work can be done on that system. And we get the formula here, work is equal to negative P delta V. So we have a pressure against which you're doing work, and delta V is the change of that volume. So this would be work caused by the expansion of a gas, or expansion of a volume of gas, by pressure internal against some external pressure, so maybe atmospheric pressure. Let's take a look at an example. How much work in joules do we need to do to inflate a 0.1, that should be 0.1 liter balloon, to 1.85 liters against atmospheric pressure? So my volume 1 is 0.1 liters, that's what I start with. Volume 2 is 1.85 liters, that's what I'm finishing with. My pressure is 1 atmosphere, that's normal atmospheric pressure, and I want to find W. Well, we know that W is equal to negative P delta V. Now our delta V is going to be 1.85 liters minus 0.1 liters. So that gives me a delta V of 1.75 liters. So I actually have all the data that I need now. So my work is going to equal negative 1.00 atmospheres, that's my P, times my delta V, 1.75 atmospheres, and I end up with a unit of 1.75 liter atmospheres. Now it's not a very helpful unit, but it is in fact a unit of work. The question asks for how much work in joules do we need to do. So we need a conversion factor, and this is the conversion factor here between liter atmospheres and joules. It's 1 liter atmosphere is equal to 101.3 joules. This is not something I expect you to know off the top of your head, and it's a value that if you need it for a problem, you'll be given it on the constant sheet. But now we can convert our liter atmospheres to joules, so we take 1.75 liter atmospheres times 101.3 joules per liter atmosphere. We see our liter atmosphere units cancel, it leaves us with joules, and we get 177 joules of work that is done. Now I should have actually carried through my negative sign. I forgot to do that here. So I would have had a negative there, negative 1.75, and I get negative 1.77 joules of work, which indicates that work was done on the surroundings by the system. Start off today talking about heat of reactions and calorimetry. Now when we're measuring the heat of a reaction, there's some things that we need to make sure that we consider about that reaction, such as if the reaction involves solutions or solids only, we usually use an open container or an open calorimeter, which means that that reaction is under constant pressure. If, however, the reaction involves the evolution of gases, we've got to use a different type of calorimeter in that measurement. We need to use something that is called a bomb calorimeter. That is a calorimeter that is sealed, and so it's used to contain the gases and all of their energy, and so that reaction occurs under constant volume. So we get a different thermodynamic value for a reaction that's under constant pressure or under constant volume. So let's talk about what a bomb calorimeter is. And so this is a calorimeter here. We've got our thermometer in there. What we've got is an insulated calorimeter here, so it prevents heat from escaping out into the atmosphere. We've got our bomb itself, which is usually made out of stainless steel. It's got a very tightly screwed on lid there. We've got wires that come down to ignite our sample that's down here. This bomb is usually pumped filled with a high pressure of oxygen. And then we've got a stir up there on top to make sure that the water remains the same temperature. And the thermometer there measures the change in the temperature as the reaction occurs. Now we're doing constant volume calorimetry. Remember, we've got our work term P delta V, but work in that case would be 0 because delta V is 0, so P delta V is 0. And so as a result, all of the energy that is coming out of that reaction comes out in the form of heat. So what we end up with for our equation is that the Q of the calorimeter is going to equal to the specific heat of the calorimeter times delta T. So we're just looking strictly at the change of temperature and the heat capacity of the calorimeter itself, and that tells us how much heat is gained by the calorimeter, and any of the heat gained by the calorimeter must have come from the reaction. So the delta, or the Q of reaction, is equal to the calorimeter, just a different sign since we have a different flow of energy. And so then we can say that the delta E of the reaction is also equal to the Q of the reaction. And that's C cal, so that's the specific heat of the calorimeter. So that's the heat capacity of the entire calorimeter and all of its components. That includes the bomb, the wires, the calorimeter itself, the insulating sleeve. So that C cal is generally something that's determined separately, experimentally, or in our problems it's something that we would be given. Now when we're in a constant pressure situation, so this would be in an open type system, our enthalpy is defined as the heat exchanged in reaction under that constant pressure. So again, open system. And enthalpy itself is an extensive property, which means that it does depend on the amount of material that we have. It is, however, a state function, which means that enthalpy is not affected by the path of the reaction. So the enthalpy of a reaction has to be examined from the point of view of the system itself. The reaction starts at reactants and it ends up as products. Now calculating the actual enthalpy of all of your different reactants and products is actually a very difficult process. So normally what we do is we report a change in enthalpy for a reaction, and that's actually fairly easy to do. When we have a change in enthalpy, we report enthalpy as H, and so the change in entropy is going to be delta H. So let's talk about delta H a little bit. So to reflect that change in enthalpy in going from reactants to products, we use delta H. And since it is a delta term, we're going to use H of our products minus the H of the reactants. Now because both of those enthalpies are in fact state functions, that means that our delta H is also a state function. And what we eventually end up with, and your book has this derivation, is that delta H is equal to the heat evolved from a reaction under constant pressure. And that little p that you see here as an annotation there, this actually means constant pressure. If it were under constant volume, then we would have Q with the little v there. Now enthalpy, H, is also defined as the internal energy plus the product of pressure and volume. So we can write enthalpy as energy plus pressure times volume. Or if we want to look at delta H, as we mentioned earlier, we can change the E and the PV term also to reflect changes. And so we would have delta E plus P delta V. Those things added together is equal to delta H. Now that P delta V term, remember, represents the energy involved in work. Now, since most of the reactions that we do are taking place in solution, and there's very little work done at all during that, especially compared to the heat evolved, that P delta V term tends to be very small, so that delta E or delta H is generally just equal to delta E, which we saw is equal to Q. So let's just summarize what we've learned about enthalpy up to now. We've got a value of delta H. It's the amount of heat either absorbed or given off by a reaction under constant pressure conditions, which is generally in an open system. If the value of delta H is positive, that means that the system has absorbed energy from the surroundings, and we're going to call that reaction endothermic. And if the delta H is negative, then the system has given off energy to the surroundings, and the reaction is exothermic. Let's look at our thermochemical equations here, and these are just reactions where we're given a delta H value, and they're reactions where heat is either absorbed or given off, and the amount of heat that's either given off or absorbed is dependent on amounts of material. The other thing we have to consider is how we're writing our reaction, because that affects the heat that is reported, particularly if we have balanced the reaction slightly differently. Let's take a look at an example of that. So here in this top reaction we have 2 moles of sodium plus 2 moles of water goes to 2 moles of sodium hydroxide plus H2. So this would be a standard way of balancing this reaction with whole numbers as our coefficients, and we get a delta H of reaction for that reaction of minus 368.6 kilojoules. Now if I decided instead to go with just lowest denominators there, and I went with 1 in front of the Na, so I divided all of the coefficients of the top reaction by 2, I end up with that half coefficient of H2. Well, it turns out if I calculate the delta H reaction for that reaction as written, since I have half amount of material, I also have half the amount of heat, and so the delta H reaction there is going to be equal to negative 184.3. So how we write our reactions is very important, and this is what makes enthalpy an extensive type property. Let's take a look at an example here. The burning of ethanol. So we have C2H5OH, that's ethanol, plus 3O2 goes to 2CO2 and 3H2O. As we would expect, that's an exothermic reaction, and it has a negative delta H that's equal to negative 1235 kilojoules. So as written, using 1 mole of ethanol and 3 moles of oxygen, I'm going to have 1235 kilojoules given off. What if we only had 20 grams of ethanol? That's far from a mole of ethanol. How much heat would we get? Well, we can calculate that just by calculating the number of moles of ethanol. So 20 grams of ethanol with a 46 gram per mole molar mass of ethanol means that I have less than half a mole of ethanol. I have 0.435 moles of C2H5OH. Now I know that I get 1235 kilojoules given off for every 1 mole of C2H5OH times my 0.435 moles of material that I actually have. So I would expect negative 537 kilojoules for a delta H when I carry out that reaction using 20 grams of ethanol. So we talked about constant volume calorimetry. We can also have constant pressure calorimetry. And this is what we see in most lab environments. And this is where a bomb calorimeter is not necessarily practical. So many of our experiments are done in calorimeters that are open to the atmosphere. If we're open to the atmosphere, we are essentially under constant pressure conditions. In these cases, we can calculate the heat absorbed or lost by a reaction occurring in solution by using the equation that the Q of solution is equal to the mass of the solution times the specific heat of the solution, for which we generally use just the specific heat of water, times the change in temperature of that solution. We can then find the heat of reaction using these relationships, where the enthalpy of the reaction is equal to the Q of the reaction, and the Q of the reaction is equal to the negative Q of the solution. So the heat that was gained by the solution had to come from the reaction, and the heat that was given off by the reaction we can equate to the enthalpy of the reaction. There is a slight error in there because it is possible that there was some work done by the reaction, but generally it's very small compared to the amount of heat that was evolved or absorbed. Now we can also manipulate our thermochemical reactions. We have to remember that the enthalpy of a reaction is in fact an extensive property, meaning that it's affected by its amounts, and we saw some examples of that. They are also affected by the direction in which the reaction is expressed. Here are a few ways that we can manipulate a reaction and how we handle the values for delta H when we do manipulate these reactions. So if a chemical equation is multiplied by some factor, then we're going to multiply the delta H by that same factor. We'll use that example that we had earlier with the sodium and water reaction. We saw that when we multiplied the bottom reaction by half, or cut all the stoichiometric coefficients in half from the top reaction, we had to cut our delta H in half as well. If a chemical reaction is reversed, then delta H just changes the sign, but the quantity of delta H, or the magnitude of delta H, remains the same. So here we have 2H2 plus O2 going to 2H2O. That has a delta H of negative 483.7. Or if we reverse that to say 2H2O goes to 2H2 plus O2, then the delta H has the same quantity, 483.7, but now it's positive because the reaction is now endothermic, but it's endothermic in the same amount that the reverse reaction was exothermic. And a more complicated process is if a chemical reaction can be expressed as the sum of a series of steps, then delta H for the overall reaction is the sum of the delta H values for all the steps that were used to make that chemical reaction. This last step is actually an entire chemical process called Hess's law. We'll take a look at Hess's law next. So we've talked about state functions before, where we've said it doesn't matter the path that a reaction takes as long as we go from reactants to products. Well, Hess's law involves the summation of heats of reaction for reactions added together to get a third reaction. So if a chemical reaction can be written as the sum of two or more other reactions, then the enthalpy of that overall reaction is the sum of all the steps' enthalpies. Let's take a look at an example. Let's use the enthalpy of formation for methane. So the enthalpy of formation is a very specific enthalpy where we are making methane from the elements in their standard state. So this would be C in its graphite form, that's the GRP, plus 2H2 gas goes to CH4. This reaction itself does not occur as written, but we need to find a value for the enthalpy of formation because that's a standard value that's often reported. Well, we can calculate the heat of reaction for this reaction by combining other reactions that we can find the enthalpy for. So let's take a look and see how we do that. So here are the three reactions that we can do to combine. We've got C graphite plus oxygen gas going to CO2. That has an enthalpy that's reported. 2H2 plus O2 goes to 2H2O. That has an enthalpy that we can report. And we have the burning of methane, CH4 plus 2O2 goes to CO2 plus 2H2O. All of these reactions occur just as written and have their delta H's measured and tabulated, and you can find them in any table of enthalpies. Notice that that third equation has the CH4 as a reactant. We're going to need it as a product because it's the product of our main reaction. So we're going to take that third reaction written up there and we're going to flip that reaction and change the sign of delta H. So we now have that third reaction, CO2 plus 2H2O goes to CH4 plus 2O2. Notice that the other reactions, the top reaction, has carbon and graphite form in the reactant, and that's where I need it. And we have 2H2s in a reactant, and that's where I need those. This third reaction has methane as a reactant, but I need it as a product. And so that's why we have flipped this reaction down here. Notice all I did was change the sign of delta H. So now I've got three reactions that's got reactants and products in the right place. And we can add up these three reactions to see what we're going to get. So let's put these together here. And we can see we've got our three reactions and three enthalpies. And we see that we've got oxygens on both sides of the arrows. Our top two reactions have oxygens in the reactant, and my last one has oxygen in the product. If you remember right, our final reaction had no oxygen in them at all. But that's okay because I can cancel these oxygens out. I've got two oxygens in the reactants, and I've got two oxygens in the product, so they cancel out. I've also got CO2 in these two of these reactions. I don't want CO2 at all, but I've got one CO2 in the product in the first reaction, and I've got CO2 as a reactant in that third reaction, and those are going to cancel out. I've also got water in the two of these three reactions, and I don't have water in the overall reaction I'm trying to find. But since I have two waters as a product in the second reaction and two waters as a reactant in the third reaction, I can cancel those out. And the only thing I'm left with is C graphite plus 2H2 goes to CH4. Well, that was the reaction I was trying to find, And since I've added up these three reactions and was able to get my overall reaction, I can now add up the delta H's, and when I do that, I get a delta H of negative 74.7 kilojoules. So even though I can't actually do this reaction, because I can find a number of reactions that when added together make that reaction, I can find their delta H. This is one of the things that lets us see that delta H is in fact a state function. If delta H were not a state function, we would not be able to do this. So these types of problems, when you're working them out, are a lot like puzzles, and they really require a lot of trial and error before you get them right. So you have to just keep at them and try to get your products and reactants correct. Now occasionally you may need to multiply a reaction or you may need to reverse it to make it contribute correctly to the overall reaction that you're trying to get. So you always have to make sure that you take that into account. Now one of the things that we need to be resolved with any of our thermodynamic data is what conditions are we making our measurements under. And so the reason we have to resolve that is because thermodynamic data changes as conditions change. And so if you want to make a table of thermodynamic data, you have to say this is the standard. It's a lot like measuring elevation of somewhere. So when we say, the elevation of Bozeman is about 4,500 feet, we know that that is above a sea level. So that's above mean average sea level. Otherwise, we could say, well, it's this high above the ocean floor. Well, it's this far below the top of Sac Peak, or whatever we wanted to do. So we've got to have a standard. So for elevation, our standard is sea level, and for thermodynamic data, we have what's called a standard set of data. And so we've got a set of conditions that we call the standard state. So let's explore that a little bit more detail. So the conditions for a standard state set of data, any gases are at 1 atmosphere. Any solutions will have a concentration of 1 molar. Temperature is generally at 25 degrees Celsius. Sometimes you'll see standard thermodynamic data for other temperatures, but that temperature does have to be stated. For our purposes, we'll see it at 25 degrees Celsius. Any elements or compounds need to be in their most stable form as well as their most stable phase for the stated temperature. So as an example, water at 25 degrees Celsius, its most stable form is water liquid as opposed to water gas. So, or if we look at carbon, the most stable form of carbon under these conditions is carbon in graphite form as opposed to carbon in diamond form. Doesn't mean that the other forms don't exist under those conditions, but we're looking for the one that is most stable. Now when we have a delta H value that is under standard state conditions, we use a little degree symbol there as a superscript. And so anytime we see delta H0 is usually how we say it. Sometimes you'll hear people say delta H naught. What we mean is that those conditions are standard state. And so if you see that little symbol there, you actually don't need to be told what the temperature is because we should know it's 25 degrees Celsius. But in addition to experimental conditions, the state of all the different reactants does have to be specified, and by this we mean the physical state. So we talked about carbon. We know that both diamond and graphite exist at room temperature, and if we look at the delta H0 for each form, what we see is that the delta H for graphite is 0, and the delta H for diamond is 1 point something, maybe 1.5 or 1.6. We know the standard elemental form for that standard set of thermodynamic conditions because that delta H will be equal to 0. So the standard elemental state for an element will have a delta H that is equal to 0. So, and when we have that, the delta H that gets tabulated, we say is a delta H of formation. And so we give it, in addition to that superscript degree symbol, we give it a subscript F to indicate formation. Let's talk about this enthalpy of formation. So a standard enthalpy of formation is the enthalpy change in the formation of 1 mole of a substance in its standard state from elements in their standard state or in their standard form. So if we were to look at a formation reaction for water, we see that we're making 1 mole of water as a liquid, because water is a liquid under standard conditions. And so to make 1 mole of water, I need 1 mole of H2 and half a mole of O2. Notice we don't normally use halves in our balancing of reaction, but because this reaction requires that I'm only making 1 mole of that substance, I have to use only half a mole of O2 to do it. So there are certain circumstances where we don't always balance a reaction with whole numbers. This is one of those times. And here we see a delta H of formation. Notice we've got that little F there, and that's equal to negative 285.8 kilojoules. And that would normally be per mole. Kilojoules per mole indicate we have 1 mole of water. Now the tabulated data that we have here, this is our standard enthalpies for heats of formation, and this is something that's actually we have in a much larger table in the back of your book. But we see anything in standard elemental state is 0. We've got Br2 in the liquid form, 0, calcium solid, carbon and graphite form, Cl2, F2, H2, N2. Those are all 0 because those are standard elemental states. And so the heat of formation for anything in its standard elemental state will actually be 0. So we've tabulated all these enthalpies of formation, and again that table I just showed you is by no means exhaustive. It goes for pages in the back of your book. But because we can do that, we can utilize Hess's law to find the delta H under standard conditions of reactions. And we use this equation here. We say that the delta H of reaction under standard conditions is going to be the sum of the delta HF of products minus the sum of the delta HF of reactants. Let's try an example, see how we do that one. And so here we have 2 carbon and graphite plus O2 gas goes to 2 carbon monoxide gas. So we're looking for the delta H of reaction here. And so we have 2 times the HF of the CO, so it's products minus reactants. And since I have 2 COs, I have to take this 2, and that goes right there. Okay, so I have the sum of my products there, minus the sum of the reactants, and so I've got to take 2 for my carbon there, and I've just got the 1 for the oxygen there. So we have 2 times minus 110.5 kilojoules for the CO, so we looked that up, minus 2 times 0 for the carbon, well, because that's elemental form of carbon under standard conditions, plus 0 for the oxygen, because O2 gas is that standard elemental form under standard conditions. So I end up with minus 221.0 kilojoules for this reaction. So that's my delta H of reaction. If we were to do a series of reactions using Hess's law, where I looked up a bunch of different reactions to add up to this overall reaction, I would actually get the exact same answer. Here's another example that will work. So we've got 2 H2S plus 3 O2, so the burning of hydrogen sulfide goes to H2O plus 2 SO2. And so we look up the various heat of formations, and for H2S it's minus 20.5. For O2 it's 0. For H2O liquid it's minus 285.8. For SO2 it's minus 296.8. So we take the sum of the products minus the sum of the reactants. And we do have to use the stoichiometry here. So if we look at this, we do have our 2 from our water going right there, our 2 from our SO2 right there, our 2 from our H2S right there, and our 3 from our oxygen going right there. And then we put in the value for those delta H that we look up, those delta HFs that we look up in a table, and we sum up the products minus the sum up of the reactants, and we end up with minus 1124.2 kilojoules. Now, the first thing we're going to look at as far as thermodynamics is the idea of spontaneity. Now, this is a term that you've probably used in everyday life for something to be spontaneous. However, this term has a very different meaning in the language of chemistry. So when we say that a reaction is spontaneous, we mean something different than what we might mean in our everyday life. So a spontaneous process or a spontaneous reaction is a type of reaction that can occur without the constant application of energy. It doesn't mean that it doesn't need a little bit of energy to get started, but once it does, it doesn't need that energy to be constantly applied in order for that reaction to continue on progressing through from reactants to products. So, and then the other thing as far as spontaneous processes is it always occurs in the direction required to reach equilibrium. And we are going to relate spontaneity and equilibrium a little bit later in the chapter. Let's talk about these spontaneous reactions a little bit. There are several common spontaneous reactions that we see, and many of the ones that we see are in fact exothermic. For example, something that burns or something that explodes, or some reaction like that. And this can lead to the incorrect assumption that only spontaneous reactions are exothermic, or the other incorrect assumption may be that all exothermic reactions are spontaneous, and neither of those are true. There are also spontaneous endothermic reactions, and there are non-spontaneous exothermic reactions. And so an example of a spontaneous endothermic reaction would be the dissolving of ammonium nitrate. When you take ammonium nitrate solid, dissolve it into water, it dissolves quite easily. You don't need to add energy to that dissolving process, and yet that reaction will be very cold. So spontaneous but endothermic. Another example is the expansion of a gas. If you go from a gas under high pressure and a low volume and allow that to go into a new volume, it will do so quite readily, and that is in fact an endothermic process that happens spontaneously. Another common spontaneous endothermic reaction would be ice turning into water at any temperature above 0 degrees. So when ice melts, that is in fact an endothermic reaction. It is absorbing energy from the surroundings, and this occurs spontaneously. We don't need to continue to add energy to that to the ice in order to get it to dissolve. But notice that it does have a temperature that makes that spontaneous. We'll talk about that a little later in the chapter as well. Now here we've kind of focused on the idea, is it exothermic or endothermic, or spontaneous or not? And we see that that endothermic and exothermic may be factors, but there are other factors other than just the heat of the reaction that are going to influence the spontaneity. Now, one of those factors is something that is called entropy. And entropy is a really kind of a complicated concept, but if we want to break it down to something a little simpler, we can say that entropy is basically a measure of disorder. So the more disordered something is, the more entropy it has. And it's given the symbol S. And so when we see a capital S in thermodynamics, we take that to mean entropy. And really what we're looking at is the energy of the system and the number of occupied available energy states versus the total number of available energy states. And so the more spread out something can be, the more spread out the energy can be, the higher the entropy for that system is going to be. Now, for the most part, we can do some visual inspections of a chemical process in order to determine the entropy change of a system. But we don't just need to look at the system. What we really need to look at for the impact of entropy is we need to look at the overall entropy changes. So not just the change of the chemical system, but also what happens to the entropy in the surroundings around the system, because they factor into the spontaneity of a reaction as well. And so we're going to look at all of that eventually. So let's just take a look at a visual inspection, something where we could look at the system itself and be able to determine is the which way the entropy goes. So let's take a look at when we dissolve potassium chloride in water. Now, potassium chloride is a salt, and so we know that when we take it out of the stockroom, it's in a crystalline form. We have that crystalline lattice of potassium and chloride ions alternating in that lattice, and that's how it is as a solid. And then when we dissolve it in water, we know it dissociates into potassium ions and chloride ions. So we took something that was very low entropy, that crystal, and we separated all those particles out, and now they're completely separated and floating around in that solution. So we've increased the entropy of the potassium chloride. However, we also have water molecules that we need to consider. They were free flowing around, and now they become bound to these new ions in there. As they become hydrated, the ions become hydrated, and they form those ion dipole interactions with the ions, and so the entropy of the water decreased, the entropy of the potassium chloride increased, and so the overall balance is something we're going to need to consider as to whether or not the overall entropy of the system, or of everything altogether, increased or decreased. But for now, we're just going to focus about the entropy of the system. So let's take a look at some examples and see what we would determine the entropy would be. So we want to predict the sign of the change in entropy in the system going from reactants to products. So in the first example here, we've got water liquid turning to water gas. We would predict the sign of the entropy change to be positive because the system becomes more disordered in going from a liquid to a gas. A gas has a lot more disorder than a liquid. The molecules are completely separated from each other, moving much faster, moving completely independently. So delta S here would be positive. Here we have an association, a precipitation reaction of silver and chloride ions turning into silver chloride. And for this, we have individual ions coming together to form a solid. So we would predict the sign of delta S here to be negative. We are losing entropy here. The system becomes much more ordered in forming that precipitate. This one's a little more difficult. We've got 4 iron solids plus 3 moles of oxygen gas going to 2 iron oxide solids, and a lot of different factors here. One of the primary factors we need to look at here is the fact that we have some gas molecules in the reactant, and all we have in the product is solid, and that's a huge change in entropy due to that phase change. And so we are also going from 7 moles of material just down to 2 moles of material, and that also represents an entropy change in the same direction, and both of those represent a negative change in entropy. The system is becoming much more ordered, either going from gas to solid or going from 7 moles to 2 moles. So we would predict the sign for this reaction to be negative, just like the reaction in the previous bullet there. Now, we talked a little bit earlier about entropy and how it really focuses on energy and the dispersion of energy among these different states. And this idea of disorder really came from a guy named Ludwig Boltzmann, and really quite an elegant mathematical system describing how energy is distributed among all of these different energy states. And really what he found is that a more disordered system has favor, and he created this concept of microstates. And what a microstate is just a distribution of energy within a group of atoms. And so there can be several different microstates that exists within a single macro state of a system. And if we take a look at a picture here and kind of what that looks like. And so here we have 4 particles, and we have 2 energy packets that can be distributed among them. And so in this first one, where we see 1, 1, we've got both energy packets on a single atom, so 1, 1. And then we've also got, in the next one, 1, 2, so we've got 1 energy packet on atom 1, 1 energy packet on atom 2. We can do 1, 3, we can do 1, 4, we can do 2 and 2, 2 and 4, etc. And so what we really see here is that if we have 4 particles and 2 energy packets, we can distribute those 8 different ways. And so that would have more entropy than, say, if I had just 1 energy packet. That could be distributed just 4 different ways. But if I had 3 energy packets, that could be distributed more ways than 8. I'm not quite sure what it is off the top of my head, but it would give us a system with more entropy. We can look at kind of the difference between macrostate and microstates in this slide here. Let me go back. There we go. And so we see here in the macrostate, really what we've got is we've got 2 particles on the left and 2 particles on the right. So we've got 4 total particles, and with 2 on the left, 2 on the right. So that's the macrostate. We haven't really considered the different ways of arranging these two different particles. And so here I can have 1 and 2 on the left, 3 and 4 on the right. I can have 2 and 3 on the left and 1 and 4 on the right, etc., so forth. And so we have several different microstates that exists within that one simple macrostate. The macrostate just indicates that I have 2 particles on both sides, left and right. Now, what Boltzmann is really known for is the Boltzmann equation, and really what this is a mathematical representation of entropy taking into account all those different microstates. And it's a very small equation, but even though it's small, it's actually quite complex in trying to apply it. But what it is S, entropy, is equal to K, which is a Boltzmann constant, times the natural log of W. Now let's take a look at what all of these are, because some of these are going to be new. And so our little k is the Boltzmann's constant. It has a value of 1.381 times 10 to the minus 23 joules per Kelvin. It is kind of a strange unit, but those are also the units of entropy, joules per Kelvin. Now the interesting thing with the Boltzmann's constant is it is in fact the gas constant, R, divided by Avogadro's number. So it's 8.314 divided by Avogadro's number, and that gives us the value of K. So this has taken this gas constant that we've used for so many different things. We've used it for energy, we've used it for gases, and now we've taken it all the way down to the atomic level, and I always find that really interesting. Now this value W here is the number of equivalent microstates that are possible within a macrostate. So the more microstates that you have available, the higher that entropy is going to go. So really what that implies is that the energy wants to distribute itself over as many atoms as possible to maximize the number of microstates, which will maximize the entropy in that system. So the second law of thermodynamics comes off of that equation, and what it says is that the total entropy of a system and its surroundings is always going to increase for a spontaneous process. So in order for a process to proceed, we have to increase that total entropy of the system and the surroundings. It doesn't mean that both of them have to increase, just the sum of them have to increase. And that brings us to a very grand, far-reaching equation here, which says that the change in entropy for the system plus the change in entropy for the surroundings is equal to the change in entropy for the entire universe. And for a spontaneous process, that means that the change in entropy for the entire universe has to be greater than zero. In other words, the change is a positive change, so that means the entropy of the universe is increasing for all spontaneous processes. Now that seems kind of silly when we're just doing a reaction in a beaker and we need to factor in the whole entropy of the universe. So it can be a little difficult to measure the entropy of the universe, and we're going to take a look at the surroundings in the system and just kind of see how it all works. But for now, we're only going to focus on the entropy of the system. We'll worry about the entropy of the universe a little bit later. So for a given temperature, as it turns out, we can analyze the entropy of the system using a fairly simple equation. That is that the entropy of the system, or the change in entropy for the system, is going to equal Q, so that's the heat involved for a reversible reaction, over the temperature in Kelvin. So delta S system is equal to Q reverse over T. So again, that Q reverse refers to the heat involved in a completely reversible process. So an example of a reversible process would be a phase change. You can go from liquid to solid, solid to liquid, liquid to gas, whatever, but it's always possible to completely reverse that reaction. There are some reactions that just simply aren't reversible. For example, the burning of something becomes very complicated because you've undergone such extreme chemical change. But a phase change makes this really easy just to look at from a theoretical standpoint. So let's calculate the delta S vaporization. So the change in entropy for a vaporization process. We're going to change 1 mole of water liquid into 1 mole of water gas or steam. So the heat involved in this process, so the delta H of vaporization, is going to be 40.67 kilojoules per mole. And we know that this process happens at 100 degrees Celsius, or 373 Kelvin. When we're using our delta S equation, we have to make sure that we're in Kelvin. So our delta S of vaporization is going to be 40.67 kilojoules per mole times 1 mole of material over 373 Kelvin. And we get a delta S of 0.109 kilojoules per Kelvin. Now, it turns out that entropy changes generally are fairly small when compared to you compare it to the heat. And so what we usually do is we express our entropies in terms of joules per Kelvin rather than kilojoules per Kelvin. So our delta S vaporization for water going to steam is 109 joules per Kelvin. Now when we look at that value, what we see is that the delta S there is positive. And this is what we would expect for a liquid to vapor phase change. Going from a liquid to a vapor is going to increase the entropy because we're becoming much more disordered and turning our water into a gas. So we see that delta S is positive. So again, one thing we have to remember is that this little calculation represents only the entropy change of the system, just the water molecules themselves. It does not include any of those effects on the surroundings. And again, we're going to focus on the surroundings a little bit later.
So if we look at entropy, it turns out that we can determine the entropy for any substance under some given set of conditions. There are some stipulations on entropy values for substances. The third law of thermodynamics states that a perfect crystalline material at exactly 0 Kelvin will have an entropy of 0. So that sort of sets the standard on where entropy values are going to start. So we never have a negative entropy. we can have a negative change in entropy, but never just a pure entropy less than zero. The most perfectly ordered crystal possible, theoretically possible, would have an entropy of zero. Anything other than that is going to have an entropy greater than zero. And since we are also always above 0 Kelvin, any substance above 0 Kelvin will have a positive entropy as well. So anytime that we raise the temperature of a substance, we're going to increase its entropy value. And this is because we're adding energy, which means that the material in the atom is going to vibrate. It's going to translate, or if we're working with molecule or atom, it's going to have more movement, which is going to increase its entropy. If we go to a phase change, we're going to go, if we phase change to a more disordered phase, that will increase the entropy. We saw that in the last lecture. Conversely, if we phase change to a more ordered phase, then we would decrease the entropy. And if we look at molecules, the more complicated a molecule, generally the higher the entropy value is going to be. You have more ways of arranging those microstates, more places to distribute energy, and we can also just look at the different arrangements that the molecule can have in space, and that's going to increase its entropy as well. So we use the idea of standard entropy values for a lot of our calculations, and all we're doing for our standard entropy values is just looking at entropy values for substances under a given set of conditions. And this is very similar to what we did with enthalpy in Chemistry 141. So our standard conditions are temperatures of 25 Celsius or 298 Kelvin. If you have any gases present or you're looking for a gaseous entropy, it's going to be under pressure of 1 atmosphere. And if you have any solutions, then their concentration is going to be 1 molar. And a lot of our standard values of entropy are tabulated. We have a small table here in the next slide. The back of your book has an extensive collection of tabulated entropy values. But here's a just a brief table from your book there. We see there that things like our gases have very large entropy values there. Our liquids are a little bit lower than that, and solids generally are a little bit lower than that as well. But there is a range in there depending on how complicated the molecule is itself. Now, when we're looking at entropy changes, which a lot of times is what we're looking at for a reaction, we can calculate the change in entropy for either a physical change or a chemical change. Now, since enthalpy is in fact a state function, we can calculate the change of entropy during a reaction by looking at the entropy of the reactants and the entropy of the products, and just taking products minus reactants. And so we have an equation here very similar to what we used for enthalpy back in chapter 10. We say that the change in entropy for a process is going to be equal to the sum of the entropy of all the products minus the sum of the entropy of all the reactants. And these little n's here indicate that we would multiply a substance by its coefficient from the balanced reaction. Let's try an example here. So we want to know the delta S, so the change in entropy for the following reaction. So we've got the burning of ethanol. So we have ethanol gas here plus 3 O2s goes to 2 CO2s plus 3 H2O gas. Now here's our equation here. We kind of work these through. We're still going to do products minus reactants, and so we look up the entropy of CO2. We see it's 213.74. We multiply it by 2 because of the 2 that is there. So that's where that 2 comes from. We look at the entropy value of water, and we have to multiply it by 3 there because of the 3 in the coefficient. Now we've got to make sure that we focus on that guy right there, that gas for the water. When you look up water in the standard entropy table, you will see a value for water in gas form and water in liquid form, and you've got to be positive that you are taking the right value. If you take the wrong value, you won't get the correct answer for a change in entropy here. And so those are our products. We're going to subtract the entropy of the reactants. And so we take the ethanol, and again, we've got a value for ethanol gas. Ethanol is also very prevalent as a liquid, so you need to make sure that you are looking up the entropy for the proper phase. And so that just has a coefficient of 1, and so we don't have any multiplier of that other than 1. And then for the oxygen, that has an entropy value as well, and we have to make sure we multiply that by 3 there because of the 3 as a coefficient. Now when we add all of that up, we get a delta S of 96.09 joules per Kelvin. So we have a positive change in entropy. It becomes more disordered as we go from reactants to products here. Well, let's expand our idea or our concept of entropy just a little bit, taking on some of the equations we looked at initially with entropy. So we had an equation that said that the change in entropy for the universe is equal to the change in entropy for the system plus the change in entropy for the surroundings. So we've seen how to calculate the delta S for that system. What we need to do is be able to figure out how to calculate the delta S for the surroundings. Well, we saw earlier that the change in entropy is equal to our Q reverse over T. Now, under constant pressure conditions, which pretty much means we have an open beaker, which is one of the most common situations that we deal with, the Q reverse is going to be equal to our change in enthalpy for the system, so our delta H. So our delta H of surroundings are going to be equal to the opposite of the delta H for the system. So, and the reason is any heat put out by the system had to be absorbed by the surroundings, and vice versa. Any heat absorbed by the system had to be put out by the surroundings. So this allows us to say that delta S surroundings is equal to negative delta H system over the temperature. So at this point what we've got is our delta S universe is equal to negative delta H system over T plus delta S for the system. Now this brings into concept this idea of Gibbs free energy, and gentlemen who developed some equations looking at this this delta S of the universe. So if we happen to take that last equation that we had in the previous slide, we're going to multiply both sides by negative T. We get an equation that says negative T delta S universe is equal to delta H system minus T delta S system. Now Gibbs defined that initial quantity there, negative T delta S universe, as the free energy change of the system, and we call that delta G. So we can substitute delta G in there and say delta G of the system is equal to delta H of the system minus T delta S of the system. And because delta G has delta S as a component, we can relate delta G directly to spontaneity. And since T is a factor in there as well, what we see is that spontaneity is actually a factor of both enthalpy, entropy, and the temperature at which the process is taking place. As far as our delta G that we calculate, if we get a delta G that's greater than 0, we would say that that reaction is non-spontaneous in the forward direction. It would be spontaneous in the reverse direction. If delta G is less than 0 or negative, then it would be spontaneous in the forward direction or non-spontaneous in the reverse direction. And if delta G is equal to 0, then we find that our reaction is at equilibrium. Well, let's explore this equation just a little bit more. So what the Gibbs free energy change really represents is the total energy change for the system. It's the energy lost in disordering the system. And it really tells us if the if the reaction has the energy to continue to disorder the universe or not. If it has energy to disorder the universe, then it will, and that makes that reaction spontaneous. And if it does not, then it will be non-spontaneous. But we can look at, using this equation, we can look at some sets of conditions that will always lead to a spontaneous reaction or always lead to a non-spontaneous reaction, or even sometimes spontaneous and sometimes not, depending on the temperature. So as an example, if we see that a reaction is exothermic, we would find a delta H is negative, and if delta S is positive, that would make our T delta S term positive, and so we'd have a negative subtracting a positive. That will always give us a negative number, so delta G would always be negative, which means that that reaction would always be spontaneous at any temperature. Well, let's tabulate some of these conditions here. So if we have an exothermic reaction, our delta H is 0, delta S is positive, that will always give us a negative delta G. So that's the condition that we just talked about in the previous slide. So if delta H is negative, delta S is positive, delta G will always be negative. If we have an endothermic reaction, and then the delta H would be positive. Now if the delta S for this reaction is also positive, we have conflicting values there. The delta H being positive, if we subtract a positive number, it depends on how large our T delta S term is. If we have a large value for T, then the T delta S term becomes larger than delta H, and our delta G will be negative. And so a reaction where delta H is positive and delta S is positive, reaction will be spontaneous at high temperatures. If T is small, then the T delta S term will not be enough to make the delta H term go negative, or for delta G go negative, and so that reaction would remain non-spontaneous with a positive delta G at low temperature. If we have an exothermic reaction and a delta S that decreases, then we have just an opposite situation from the previous set, and at high temperatures the T delta S term will dominate, and that becomes you're subtracting a large negative number, so adding a positive number. And if that number is large enough, it will take the negative delta H and turn it into a positive delta G. So exothermic with a decrease in entropy indicates that we have a positive delta G at high temperature, or a negative delta G at low temperature. So it would be non-spontaneous at high temperatures, but spontaneous at low temperatures. And then if we have an endothermic reaction that has a decrease in entropy, then that reaction will be non-spontaneous at all temperatures, because those values will always be positive. Well, here's an example that we can do, and we will work this one out in class. Well, let's see how we can calculate delta G0. And that little zero indicates that we're under standard states. So we've seen how we can calculate delta G using delta H0, delta S0, and T. We've also seen how spontaneity is a function of the temperature sometimes. So if we happen to be calculating delta G at 298 K, then we make that a set of standard conditions. And so we create delta G0 or delta GF0 values for these standard conditions into our table, and we use an equation very similar to the one we used to use for delta H and delta S. And we have delta G0 is equal to the sum of our delta G's of the products minus the sum of the delta G's in the reactants. So again, products minus reactants, where the n's there represent the stoichiometric coefficients in front of each substance. So here's an example that uses the exact same reaction that we had earlier using delta H's and delta S's, but here we're going to use it with our delta G's. So let's talk about how we interpret this value of delta G. And we've looked at the sign of delta G and seen how it can predict the spontaneity of a reaction. And the other thing that we can use delta G for is to look at the size of the delta G, how positive or how negative it is. And that can tell us something about where the equilibrium lies. If we have a really large negative delta G, it indicates that the equilibrium is far to the right and so very much favors the products. And if we have a large positive delta G, it indicates that equilibrium is reached with primarily reactants left in the mixture there. If we have a moderate-sized delta G, either positive or negative, it indicates that the equilibrium is somewhere in the middle. Obviously, if it's a negative delta G, even moderately sized, it indicates it's a little bit farther towards the products, and if it's a moderate positive delta G, it's a little bit more towards the reactants there. Now, there's a significant relationship between delta G and equilibrium, not only qualitatively, as we just saw, but also quantitatively. We saw earlier that when delta G is equal to 0, our reaction is at equilibrium, and the farther away delta G is from 0, the farther away from equilibrium that reaction is going to be.